Welcome to Advanced Group Theory. Today, we are diving into one of the most fascinating and foundational topics in abstract algebra: finite simple groups. These unique structures are the fundamental building blocks of mathematical symmetry, and understanding them unlocks the deep secrets of both pure mathematics and the physical universe. Let us begin our journey. To begin understanding this topic, imagine you are building a massive, incredibly complex castle out of Lego blocks. No matter how huge or intricate the castle is, if you break it down completely, you are eventually left with indivisible, solid Lego bricks. In advanced group theory, mathematical structures called groups are exactly like these Lego structures. We can break some complex groups down into smaller, simpler pieces called normal subgroups. But eventually, we hit certain groups that absolutely cannot be broken down any further without destroying them. Now that we understand the idea of breaking groups down, let us define this formally. A normal subgroup is a perfectly balanced smaller group inside a larger one. Every group automatically has two obvious normal subgroups: the trivial group, which contains only the identity element, and the entire group itself. A finite simple group is defined as a group that contains exactly and only these two normal subgroups. It lacks any proper, non-trivial normal subgroups. If you try to break it down, you either get the exact same group back or you destroy it completely. This brings us to the formal mathematical statement of simplicity. Conceptually, this formula just translates our Lego brick idea into rigorous algebra. It states that if the variable n is a normal subgroup of the main group G, then n is strictly forced to be either exactly the trivial group E or exactly the entire group G. There are absolutely no other options allowed. If this strict condition holds true for every possible normal subgroup you can find in G, then G earns the title of a simple group. If the size of G increases, this unbreakable rule must still hold. Before we move on, let us see this with a concrete visual. On the left, you see a complex group. When we apply mathematical operations to break it down, it shatters into smaller, interconnected normal subgroups. But look at the simple group on the right. When the hammer of algebra strikes it, it repels the attempt. It stands as a single, unified mathematical object. This unbreakable nature is exactly why mathematicians spent decades hunting down and categorizing every single finite simple group in existence. Now that we have our definition, let us look at a powerful mathematical tool called Lagrange's theorem. Conceptually, this theorem tells us that the size of any subgroup must perfectly divide the size of the entire group. In our formula, the vertical bars denote the order or size of the group. So the order of n must divide the order of G evenly. If the order of G increases, the possible sizes for n must scale accordingly to remain perfect factors. We will use this strict divisibility rule to prove a fundamental property of prime-ordered groups. Let us apply Lagrange's theorem to prove that any group with a prime number of elements is automatically a simple group. This chunk of the proof is setting up our basic variables. We start by setting the order of our main group G to be a prime number, which we call P. Next, we introduce a normal subgroup called N. According to the theorem we just saw, the size of n must be a perfect factor of the size of G. This means the mathematical order of n must divide our prime number P without leaving any remainder. This setup is crucial for what comes next. Continuing our proof, we must now consider the mathematical properties of a prime number to reach our final result. By definition, a prime number can only be divided by 1 and itself. It has absolutely no intermediate divisors. Therefore, the size of our subgroup n is strictly forced to be either exactly 1 or exactly p. If the size is 1, it can only contain the identity element. If the size is P, it contains every single element, making it the entire group. Since these are the only two mathematical possibilities, the group lacks any proper non-trivial normal subgroups. This definitively proves that all groups of prime order are simple. So, we have proven that prime-ordered groups are simple. This brings us to the opposite question. How do we prove a group is not simple? To do this, we only need to find a single proper non-trivial normal subgroup. We achieve this using Silo's third theorem, which helps us count specific subgroups called Silo P subgroups. A fundamental rule states that if a group contains exactly one unique Silo P subgroup for a specific prime, that subgroup is mathematically guaranteed to be a normal subgroup, which shatters the simplicity of the main group. Let us look at the formula for Silo's third theorem by analyzing a group of order 15. Conceptually, we first factor the total size into its prime components, giving us 3 and 5. The theorem dictates two strict conditions to find the number of Silo 5 subgroups, represented by N5. First, N5 must evenly divide the other prime factor, which is 3. Second, N5 must be congruent to 1 modulo 5, meaning it leaves a remainder of 1 when divided by 5. Both conditions must be satisfied simultaneously. Let us apply this formula to see if a group of order 15 is simple. We are given the size of the group and asked to find if a normal subgroup exists. We start by finding a number that satisfies both of Silo's conditions. The only positive numbers that divide 3 are 1 and 3. When we test 3, we see it leaves a remainder of 3 when divided by 5, so it fails. However, testing 1 shows it leaves a remainder of 1, perfectly satisfying the modulo condition. Continuing our example, we found that N5 equals 1. This means there is exactly one unique Silo 5 subgroup in the entire group, which we will call P. Because it is unique, group theory guarantees that P is a normal subgroup. We also know its size is exactly 5 elements. Since 5 is not 1, it is not the trivial group, and since 5 is not 15, it is not the entire group. We have successfully found a proper non-trivial normal subgroup. Physically, this means the group can be broken down, so it cannot possibly be a simple group. Now that we have used these theorems, let us understand why finite simple groups matter in the real world. Through the Jordan-Holder theorem, mathematicians proved that every single finite group can be broken down into a unique list of finite simple groups, exactly like factoring an integer into prime numbers. In the real world, this is the mathematical language of symmetry. Chemists use it to predict how molecules react and vibrate. Physicists use it in quantum mechanics to classify the fundamental particles and forces that govern our universe. We have covered the full topic of finite simple groups. Let us review the most important ideas. First, finite simple groups are the fundamental, indivisible atoms of mathematical symmetry. Second, they are defined by their absolute lack of proper non-trivial normal subgroups. Third, we saw how Lagrange's theorem guarantees that groups of prime order are always simple, and how Silo's theorems help us break down complex groups. You now understand the foundational building blocks of group theory. Excellent work!